Alrighty, so after looking at naming and wrapping that up, and I've posted the old videos on that, I don't want to redo it. So with the other new stuff we looked at, in addition to just kind of the generic stuff with the the little details from the book, was looking at homologous series. That's really the big deal that we didn't cover in 10.1. And so we learned that homologous series, like I say here, it's a set of compounds with the same functional group and basic structure, differing only by the length of that carbon chain or by the number of CH2 groups. So you see from my aldehyde homologous series that I have at the top here, the only difference between each of these successive compounds is a CH2 group. So that's the fundamental difference there. We saw that these homologous series can be represented by the generic formulas or the general formulas for the compounds. And so, there's a few of them listed here. You can figure all of them out, just create a very simple version of whatever the kind of compound that you're looking at is, and you can figure out that generic formula. So then, because depending on the number of carbons, that will influence the number of hydrogens. So you just adjust that formula under hydrogens and add anything extra on the end, and you get your general formula. We saw that we started talking about intermolecular forces, and we saw that there will be a trend in the physical properties for the homologous series, right? As those molecules get bigger, their dispersion forces will increase because of the length of that chain, and therefore their boiling point will increase and their volatility will decrease. And we also saw that since they have the same functional group, and we just talked about the fact that the functional groups is where the science or where the chemistry happens, that they should all have similar or identical chemical properties. So that kind of came up as well. Okay, so then we reviewed the different types of formulas. So of course we have our traditional empirical and molecular formulas. Those are going to come in handy later on when we get into spectroscopy. And then for organic, we really realized that the molecular formula, while it works well for small molecules and for non-organic molecules, once we get into organic chem, we need the structure because things could be connected so very differently, right? That's one of the things that makes organic chemistry such a vast study is there is almost an infinite number of organic compounds out there because you can just rearrange them. So we see that we use what's called a structural formula, and that's going to show exactly how the atoms are bonded together, and that's what we need to know, chem. We need to know exactly the way that they are connected. So we have a few different versions, and you need to be able to do all of these. So your full structural formula, this is kind of the most informative, but also the most annoying because you're drawing all those bonds. So if you imagine if you have a long chain, that's a lot of bonds to hydrogen, but you have to be able to do it. So if you're asked to do a full structural formula, it should look like the one in red here with all the bonds shown, every single one. Your condensed formula, which I have written in blue here, that's where you're omitting all the bonds. And all you're doing is you're showing, starting from the beginning of the molecule to the end, first carbon, what's it attached to? Second carbon, what's it attached to? Third carbon, what's it attached to? Fourth carbon, what's it attached to? And so on and so forth. So you really have to be careful. Remember, when you're doing naming or structure drawing or finding out information about a compound, if you're given that condensed structural formula, I really recommend you open that up and draw either the full formula or a hybrid formula, more like the ones I regularly draw in class. And this is giving truly the minimum amount of info that we need to know, right? By understanding the way that condensed formula is drawn, we are able to know exactly how that molecule is put together. And then the bottom one there is your stereochemical formula, and you need to be familiar with this and be able to draw these. And this is just basically your VSEPR theory drawings, right? But now we're applying it to this larger molecule. And this is where you're showing the three-dimensionality. So notice on this one how I was pretty strategic to get as many of my bonds as possible in the plane of the paper. That way you have as many just normal lines as you can possibly have, and then you have just less of the dashes and the wedges going in and out of the paper. And notice I'm showing, relatively speaking, what those bond angles are, right? That first carbon is going to have a tetrahedral arrangement around it, and we see the tetrahedral arrangement of those bonds. The second one is going to be trigonal planar. It has 3 electron domains. So I'm showing those bonds in as close as I can manage a trigonal planar fashion with that 120-degree bond angle. And then the last one with the OH, we know that it's a tetrahedral electron arrangement around that oxygen, but we have the lone pairs, so it results in that bent shape. So you're really trying to show the shape of the molecule. It's kind of the closest you can get to drawing those molecular models and getting it on paper. You want to do this if you're trying to show those models, as opposed to doing, I saw some of you doing like the ball and stick kind of drawings. Those are going to get messy real quick. If you want to show three-dimensionality, I recommend you work on doing these stereochemical formulas. And then here we go. So these are the last couple formulas. So right, for me, I'm going to do, and this is the same molecule that was on the other page, I'm going to do a hybrid, right? I'm going to do basically a condensed formula, but then I'm going to show anything funky, right? If there's a double bond, if there's, you know, a carboxyl group or a carboxylic acid group, sorry, I'll show that part. If there's, if there's different elements bonded, whatever, anything that is different from just a straight chain hydrocarbon, I'm going to show that. And that allows for a little bit more of a condensed thing. I'll sometimes do a little bit more like a full structure, but without showing all the bonds to hydrogen. I'll just write those CH3s or CH2s or whatever and not show every single bond to hydrogen, because it gets old pretty quick. And then the last one here, the skeletal structure, that one, remember, you do not get to use this as performance when you're doing assessments and stuff. You don't get to write these, but you absolutely need to understand them, right? So remember, with those skeletal structures, when you're looking at those lines, if there's the end of the line with nothing on it, like on the left side of this molecule, there's a carbon there. If there's a bend in that line, there's a carbon there. That's it, right? On the right-hand side, the stick ends, but there's an O. There's no carbon between the stick and the O, right? This molecule has two carbons in it, and the one that's double bonded to the oxygen is also bonded to that other oxygen, right? So you're just showing elements that are parts of a functional group, or that are, you know, that are different than carbon and hydrogen. And then anywhere that hydrogens would fit, you must assume that they are there. So we need to look at this and understand that at the end of that stick on the left-hand side, there's a carbon, and there is also 3 hydrogens. It's a really easy spot to screw up if you're asked how many hydrogens are there. I believe you had one of those on your ALT4 test, where you have to remember, oh yeah, assume the hydrogens wherever they can fit. So be careful when looking at those. So that gets us basically through page 316, and that's where I said we would just kind of stop for now. Next class, we'll wrap up 10.1 pretty quickly. There's hardly anything there. And then we'll do a little bit more modeling in class, and then I've got the project for you. So be sure to check out the other videos that I'm going to connect onto the page for naming. I've got those 2 older videos. I'm just going to link those directly on your page. You can also find them at the Risk Science website. All right. I hope you enjoyed. I don't think I have any. So we'll do that in class. Sorry. All right. We're done. See you later. Bye-bye.